If Christopher Columbus hadn't, completely botched a 1,000-year-old math equation, he never would have sailed west to discover the Americas.
Yeah, he simply wouldn't have even tried.
Right. Welcome to today's deep dive. Whether you are commuting, maybe prepping for a meeting, or you just have this insatiable curiosity about human ingenuity, you are in the exact right place.
Absolutely.
Our mission today is to shortcut your way to being well-informed about how ancient and medieval minds solved these just monumental problems. We are looking at a stack of really fascinating sources today,
Yeah, we've got some comprehensive historical records on geodesy.
which is the science of measuring the Earth, for anyone wondering.
Right, exactly. Along with detailed engineering accounts of the 12th century Muslim polymath al-Jazari. Plus, we're unpacking a really provocative academic paper by Paul Keyser.
Yeah, that paper completely rewrites the history of Hero of Alexandria's ancient steam engine. It's wild.
We are going to look at the underlying logic of these discoveries, because the goal is to figure out not just what these thinkers built, but how they operated, and why modern history has, well, in many cases, completely misunderstood what they were actually doing.
Okay, let's start with the macro. Like the absolute biggest picture possible, the Earth itself. Because it's a super common myth that everyone in antiquity thought the world was flat.
Oh yeah, completely false.
Right. Early thinkers had already figured out the Earth was a sphere using pure naked eye observation.
Yeah, going back to the ancient Greeks, you see thinkers like Aristotle noticing that during a lunar eclipse, the shadow the Earth cast on the moon was, always curved.
Oh, yeah, that makes total sense.
And he also pointed out that as you travel south, the constellations in the night sky actually change. So stars you could easily spot in Egypt, well, they weren't visible when you traveled further north.
And sailors knew it too, right? Like, if you are standing on a dock, you see the top of an incoming ship's mast appear over the horizon long before you see the wooden hull.
Exactly. That only makes physical sense if the ship is sailing over a curved surface.
But I mean, knowing the planet is round is one thing. Figuring out exactly how big it is, that is an entirely different level of problem solving.
It really is.
And that brings us to Eratosthenes in the 3rd century BC. Okay, let's unpack this for a second. Measuring the entire planet with just a stick and a shadow is like figuring out the exact dimensions of a football stadium using only a matchstick. It's mind-blowing.
It's a massive leap of geometrical genius.
Well, wait, I'm trying to visualize this. He's looking at a shadow in one city and a well in another. How does that actually help him calculate the distance of the entire planet?
So Eratosthenes knew of a very specific well in the city of Syene, which is modern-day Aswan in Egypt.
Oh.
And at local noon on the summer solstice, the sun shone straight down to the absolute bottom of that well.
So no shadows were cast anywhere in the city.
Right, none. The sun was perfectly directly overhead. But Eratosthenes was living in Alexandria, much further north. So he set up a vertical rod, known as a gnomon, and observed that on that exact same day, at the exact same time, the rod in Alexandria actually did cast a shadow.
Because the Earth is curving away from the sun. I mean, the sun can't be directly overhead in both places at once on a curved surface.
Exactly. What he realized is that because the sun is so incredibly far away, its rays hit the Earth essentially parallel to each other. By measuring the angle of the shadow cast by his stick in Alexandria, he found it was about 7.2 degrees.
Okay.
And if you do the geometry, 7.2 degrees is exactly 1/50th of a full 360-degree circle.
Oh, wow. Let that sink in for a second. So if the angle of the shadow is 1/50th of a circle, then the physical distance between Alexandria and Syene must be 1/50th of the Earth's total circumference.
You got it. He just needed to know the physical distance between the two cities.
Right. So how did he figure that out?
Well, he hired professional surveyors called dogmatists. They were essentially guys trained to walk with perfectly equal measured paces. They marched through the desert and measured the distance. He multiplied their total distance by 50, and his final calculation was only off by about 1 to 5% from the actual modern measurement we use today.
1 to 5%. Using a stick, a well, and some guys piecing through the desert, that is insane.
It really is.
But here's the crazy part that brings us back to Christopher Columbus. Humanity actually lost this accuracy. Centuries later, astronomers like Ptolemy and Posidonius decided to crunch the numbers again, and they got a much, much smaller Earth.
What's fascinating here is how scientific knowledge isn't always a straight line of forward progress. Eratosthenes had it essentially perfect, but the scientific consensus regressed to this smaller Earth model.
Which is wild.
Yeah, and that mathematical regression had massive historical consequences.
Right, so fast forward to Columbus trying to sail to Asia. He looks at these later deeply flawed maps. And to make matters even worse, he uses calculations from a 9th century Persian astronomer named Alfraganus.
Yeah, and Columbus completely misunderstands the units of measurement. He assumes Alfraganus was using Roman miles when the astronomer was actually using Arabic miles, which are, significantly longer.
So Columbus accidentally shrinks the globe even further in his own mind. He calculates a distance to Asia that is a full third smaller than reality.
Exactly.
I mean, if Columbus had actually believed Eratosthenes' highly accurate numbers from over a millennium earlier, he never would have sailed west. He wouldn't have even tried because he wouldn't have had the funding, the food, or the supplies to survive the true distance to Asia. A math error accidentally led to the European discovery of the Americas.
It just highlights how the application of knowledge, even flawed knowledge, shifts the entire course of human events. Once humanity mapped the boundaries of their physical world, the next logical step was trying to manipulate it. We move from the math of passive observation to the physics of motion and environment.
And that means we are heading straight into the Islamic Golden Age. The sheer leap in practical engineering during this period is just staggering.
Oh, absolutely.
Speaking of measuring the Earth, we have to mention Abu Rayhan al-Biruni in the 11th century. He basically looked at Eratosthenes' method of hiring guys to walk across the hot Egyptian desert and was like, no thanks, I can do this without the cardio.
Yeah, al-Biruni fundamentally changed the methodology by applying spherical trigonometry. Instead of walking between two cities, he found a tall mountain in India overlooking a flat plain.
Okay, so he's up on a mountain.
Right. He measured the exact height of the mountain. Then, standing at the peak, he used an instrument called an astrolabe to look straight out at eye level and then measured the angle down to where the horizon line visibly curved away.
Picture yourself standing on that mountain. You look straight ahead, then you tilt your head down to see the edge of the Earth. That angle of your head tilting is the dip angle, right?
Exactly. By knowing the height of the mountain and that specific dip angle, al-Biruni created an imaginary right triangle connecting his eye, the horizon, and the exact center of the Earth's core.
Wow.
Yeah, it allowed one person from one single location to calculate the Earth's radius with incredible geographical precision.
Working smarter, not harder. But where this era truly explodes is when these thinkers start automating life. Enter Ismail al-Jazari, born in 1136. He is widely considered the father of robotics.
A true pioneer.
He wrote this massive, incredibly detailed manuscript called The Book of Knowledge of Ingenious Mechanical Devices. When you read what this guy built, I mean, it genuinely feels like time travel.
Al-Jazari was a polymath, but fundamentally he was a master engineer and artisan. He wasn't just theorizing on paper, he was physically building these things.
Yeah.
He's credited with inventing the camshaft and the crankshaft.
Okay, we really need to pause on the crankshaft because if you look under the hood of your car right now, you are looking at Al-Jazari's conceptual DNA.
Totally. A crankshaft is a mechanism that converts rotary motion, like a wheel spinning in a circle, into linear reciprocating motion, like a rod pumping up and down.
Like the pedals on a bicycle.
Exactly like that. Your legs push up and down in a linear motion, and the crank translates that into a spinning circle to turn the wheels. Al-Jazari engineered this to power a double-action suction pump with valves, moving water out of rivers with an efficiency that was just unheard of at the time.
And he also invented the camshaft. So picture a spinning metal rod, but instead of being perfectly round, it has a teardrop-shaped bump on it. That's the cam.
Right.
As the rod spins, that teardrop bump comes around, pushes a lever or a valve open, and then lets it drop down as it keeps spinning. He used these components to create automata, like machines that moved and operated entirely on their own.
He was synthesizing earlier Greek and Islamic knowledge, but adding crucial, highly practical elements to make these devices robust.
The automata are wild. He built an automated hand-washing servant that would offer soap and towels to guests, which actually featured an early flush mechanism.
Yeah, and an intricate elephant clock.
But here's where it gets really interesting. He built a physical wooden boat carrying a 4-person robotic band. It floated on lakes to entertain royal guests.
which is just incredible to picture.
It was driven by the flow of water pushing a series of pegs and cams that operated percussion instruments. By taking the pegs out and moving them to different slots, you could actually change the rhythm the robots played. It was effectively a 12th century programmable drum machine. You were basically inserting physical punch cards.
It really was an early form of programming.
But wait, I have to push back a little here. Weren't a lot of these devices just like fancy party tricks to get the king's guests drunk and entertained?
I mean, yes, many of these automata were specifically commissioned for royal banquets. But to dismiss them as mere party tricks is to miss the engineering profoundness beneath the surface. While the end-user experience was entertainment, the construction required breakthroughs in practical application.
Oh, interesting. Like what?
For example, Al-Jazari was introducing the lamination of timber.
Which is basically gluing thin layers of wood together with alternating grain directions, right? So the wood doesn't warp or bend when it gets wet in these water clogs.
Exactly. He also pioneered the static balancing of wheels. That means ensuring the weight of a wheel is perfectly evenly distributed so it spins smoothly without wobbling and tearing the machine apart.
Oh, okay.
He used paper models to test his designs before building them in brass or wood, and he ground his valves with emery powder to create perfectly watertight seals. He bridged the gap between the dramatic, almost magical illusions of earlier Greek inventors and highly practical, robust engineering.
So the toy is just the friendly user interface for a mechanical revolution. And that leads us perfectly into the final and maybe most mind-bending source in our stack. Let's look at one of the most misunderstood inventions in human history. Heron of Alexandria's so-called steam engine, known as the aeolipile, built way back in the 1st century.
Yes. For over 100 years, modern historians have pointed to this device in absolute bewilderment.
For those who haven't seen a diagram, Heron's device was essentially a closed cauldron of water heated over a fire. Steam rose through vertical tubes into a hollow metal sphere mounted above the cauldron.
Right.
The sphere had 2 bent nozzles protruding from opposite sides. As the steam shot out of the nozzles, the sphere spun around on its axis. It was steam power in the 1st century. And modern historians like Wilamowitz and Marie Boas Hall, they've completely mocked it.
Yeah, they called it a mere Spielzeug, a toy. Or they called it a badly designed, highly inefficient engine.
Which inevitably leads to the classic, frustrating historical question. If the ancient Greeks had steam power, why didn't they have an industrial revolution?
People assumed the Greeks were just lazy, or they somehow missed the obvious potential of hooking a train up to it.
Right. But we are relying on Paul Kieser's brilliant academic paper here, and he completely dismantles this assumption. Kieser's thesis is that Heron's device wasn't an engine at all. It was never meant to generate power to lift things or turn gears.
No, it wasn't.
It was an autokinetic sphere, a crucial scientific experiment specifically designed to disprove Aristotle's laws of physics. So what does this all mean? Judging Heron for not building a steam train is like finding a primitive battery in an ancient ruin and asking why they didn't invent the smartphone. It's total anachronistic retrojection.
If we unpack that term, anachronistic retrojection means we are unfairly taking our modern obsession with capitalism, efficiency, and industry and projecting it backward onto a culture that just didn't view the world through that lens.
We are grading them on a test they weren't even taking.
Exactly. This raises an important question, though. If it wasn't an engine, what exactly was Heron trying to prove with this spinning metal ball?
Right. What was the point?
To understand this, we have to look at the reigning physics of the day, which belonged to Aristotle. Aristotle stated that for any object to move, it required an external supporting medium to push against. Motion required external friction or resistance.
Oh, this is Aristotle's famous boat analogy. He said that a person sitting inside a sailboat cannot move the boat by blowing air from their own lungs into the sail from the inside.
Right, because you have to push against something external to move.
Okay, so how does Heron's device fit in?
Heron's spinning sphere completely defied this law of nature. Think of a spinning lawn sprinkler, but instead of water shooting out the bent arms, it's high-pressure steam. The sphere was moving rapidly, but what was it pushing against? Nothing external.
It was moving via internal recoil.
Yes. It is what we would eventually formalize centuries later as Newton's third law of motion. Every action has an equal and opposite reaction. The steam shooting out one way caused a recoil that spun the sphere the other way. Heron was demonstrating that motion could happen without external resistance. It was a high-level physical counterexample to Aristotle's foundational theories.
So it wasn't a failed train engine. It was a wildly successful physics experiment. It is literally the earliest physical demonstration of the rocket principle.
Exactly.
But, okay, if Heron was conducting physics experiments on this advanced level, it brings us back to that nagging question. Why didn't ancient technology advance faster? Like, if they understood steam recoil and they had advanced gears, why didn't they combine them to make factories?
Yeah.
Let's unpack the myth of the blocked industrial revolution.
Yeah, one of the most common arguments you hear is the class structure, or Marxist argument. This theory claims that the widespread availability of slave labor in antiquity prevented the need for labor-saving machines.
The logic goes, why invent a steam pump if you have 100 enslaved people to carry water for free?
Right. But Kieser dismantles this idea impartially. History shows us that machines actually make slave labor more efficient and profitable for the owners. Kieser uses the example of the cotton gin in the American South.
Oh, wow. Yeah, the invention of the machine didn't eliminate slavery. It expanded it exponentially because it made the processing of cotton incredibly fast and lucrative.
Exactly. Or look at the Roman slaves using complex water wheels in Spanish silver mines. The existence of slave labor doesn't inherently preclude industry or mechanization.
So that argument just doesn't hold up.
No. The other misconception is that inventions just magically appear as sudden aha moments. Technology evolves slowly, through iterative steps. Heron's steam device didn't just pop out of nowhere into a vacuum. It was part of a slow, logical evolution of pneumatic devices spanning centuries.
And Kieser traces this lineage beautifully. Like, in the 5th century BC, Hippocrates used an inflatable bladder to test how materials precipitate and flow.
Right.
Then, Stratton built a hollow bronze pressure sphere to physically prove that air could be compressed. Then, Philon invented a thermoscope, which used temperature changes to create a vacuum and move water. And then Heron refined all of this into a water squirt device, and finally, the steam spinning sphere.
It's a clear evolution of thought.
But it's so tempting to look back and think they were just like one gear away from building a locomotive.
If we connect this to the bigger picture, if Heron had wanted to create a steam turbine to generate motive power to grind grain or lift weights, he absolutely could have.
Really?
Yes. He already knew about vaned water wheels. He knew about windmills. He purposefully built a sphere because a sphere is the best geometric shape to withstand immense internal pressure without bursting. If you want to turn a heavy gear, a sphere is a terrible shape to use.
Right. I mean, you can't easily attach a drive belt to a perfectly round ball.
Furthermore, the joints of his device would have leaked steam terribly under load, and the sphere itself was spinning at something like 1,000 revolutions per minute.
Oh, wow.
That is way too fast for ancient wooden or brass gearing to handle efficiently. The gears would have shattered. He built it exactly the way he needed it to be built for a frictionless physics demonstration.
So we have basically been looking at ancient history through the lens of the 19th century Industrial Revolution and judging them for lacking our specific commercial ambitions.
The epistemological conclusion here is vital. Epistemology is just the study of how we know and what we value as knowledge. Ancient science wasn't always about power, efficiency, and commercial industry. It was often purely about understanding the universe.
Like pure physics.
Exactly. When Galileo dropped weights from the Leaning Tower of Pisa, no one criticized him for not hooking those falling weights up to a crank to grind wheat. He was doing pure physics. Heron was doing the exact same thing. Building up the theoretical framework of physics is a slow, methodical process that precedes application.
It completely changes how you view human history. These weren't primitive people stumbling around in the dark waiting for someone to invent the steam engine. They were mapping the cosmos with stunning accuracy, building programmable machines, and arguing advanced fluid dynamics.
It reminds us that our current technological paradigm, where every discovery must have an immediate, practical, monetizable application, is just one specific way of interacting with the physical world. It is not the only measure of progress.
Well, we have covered a massive amount of ground today. We've gone from the macro geometry of the planet to the micro recoil of steam molecules. The next time you pull out your phone and rely on GPS to find a coffee shop, take a second to remember Eratosthenes, a guy with a stick and a shadow, mapping the globe so well that a math error 1,000 years later changed the world.
Yeah.
And the next time you turn the key in your car and hear the engine roar to life, tip your hat to Al-Jazari and the teardrop-shaped cam and crankshaft humming under your hood.
The foundations of our modern world are built entirely on the quiet, often misunderstood brilliance of these ancient and medieval thinkers. They were solving the universe's puzzles with whatever they had on hand.
Which leaves us with one final thought for you to ponder. For centuries, modern historians looked at Heron's incredible physics experiment, literally the earliest demonstration of rocket propulsion, and they arrogantly dismissed it as a toy because it didn't look like their massive, clanking industrial machines.
Right.
So look around you today. What current toys, video games, or seemingly trivial internet experiments might actually be holding the hidden keys to the next major scientific paradigm shift? Keep questioning the world around you, and we'll catch you on the next deep dive.